All right. Hello, everyone. Um, Welcome to the lecture number 11 of our quantum basics of quantum computing course. And let us quickly recap of what we've done last week. So our last lecture was dedicated to the in detail discussion of this Grover's search algorithm. And so I decided to discuss this quantum algorithm in more detail way because it is I believe, one of the most important algorithms. And today we will discuss some other quantum algorithms in less detailed way. All right, so the discussion of the Grover's search algorithm, we started from the way how we represent this perfect superposition state of a n qubit system. Okay, so here is the formula for this superposition state, and this superposition state is one of the most important components of the Grover's algorithm. Okay, so in a nutshell, the Grover's algorithm is basically the rotation of this superposition state over the orthogonal state to the one we searching for. Okay, so this omega state is the state we're searching for, and we form the orthogonal state to the state omega, and first rotate the superposition state over this orthogonal state, and then once again rotate this resulting state over the vector S. And this operation applied several times leads or rotates this resulting vector closer and closer to the state we are searching for. Okay, so in general case, this operation, this Grover's iteration, must be supposed to be applied several times. Okay, and this operation consists of two unitary operators. One is the oracle, which is to be programmed to, for the searching for the particular state omega, and another one is amplifier, which is pretty much the same for any circuit, for any Grover's particular algorithm. Okay, so we discussed all this in detail, including this part about the programming the oracle's operator, oracle's operator. And we also discussed the number of iterations to be done in order to find the elements. So, for example, in the system of different elements n, the number of iterations is equal to the square root of n. And it is drastically different to the number of classical search iterations, which is roughly n over 2. Okay, so it's using this algorithm, we get the quadratic speed up of the search. And as an example, we discussed this 2-qubit example of the Grover's algorithm, and we designed the circuit that enables the search for the state 1, 1, for the state 1, 1. So for the state 1, 1, the oracle is particularly simple. It is just the control Z gate. And then for the 2-qubit system, square root of 2 is about 1. So we need just one iteration to get the result. All right, so let me continue, and so the first the first algorithm that we're gonna discuss today is gonna be this Deutsch algorithm. Deutsch algorithm. So first of all, it's a lecture number 11, and the topic is 4.4. Deutsch algorithm. The Deutsch algorithm. Um, so the Deutsch algorithm is, I would say, less useful. And in fact, today, this algorithm is used for benchmarking the quantum machines, quantum computers. At the same time, this algorithm is very illustrative. So it nicely illustrates the how we use the quantum properties of a quantum system, quantum computer, in order to do something useful in a very efficient way. Okay, so this is the first quantum algorithm to be proposed that demonstrates that demonstrates a that a quantum computer can be more efficient than a classical machine. Okay, so this is the first quantum algorithm proposed. And in order to, before we discuss the algorithm itself, let us start from the statement of the Deutsch problem. So the algorithm is supposed to be like used for solving some kind of a problem, right? So in this case, we have this Deutsch problem. And the Deutsch problem is one of the so-called black box problems. Black box problem. And it is stated as follows. So suppose we have a function, a binary function, f of x. So this is the binary function. Binary means that this x can get the argument can be 0 or 1. 0 or 1. Okay, and it works as follows. So this function gets zeros and ones as the input, and it returns either 0 or 1 in the output. Okay, and here we have 4 possibilities, right? So for example, if f0 or f1, we have 4 different types of the function. Okay, so for example, if f0 returns as 0, and if f1 returns as also 0, this is one type of the function. And also, if this one is 1 and this one is 1, this is another type of the function. And we also might have this type of function and this one. So there are two types of the function here. The first and the second one, these two are constant functions, meaning that we provide 0 to the input and it returns as 0 to the output, and it doesn't depend on 0, either 0 or 1 I give it to the input, right? So the output is always either 0 or 1. So this type of the function is constant. But the second type of this function, which depends on the argument, is called balanced. Balanced function. Okay. So sometimes the functions like this one is called oracle. Because it gets something in input, like a request. We ask the function and it returns either 0 or 1 as an output, like an answer to our question. And let's suppose that we have a function, but we don't know the type of it, the type of this function, the type of the function we have, and we need to define it. So suppose we don't know the function. Need to define it. Need to define it. So from a real life, what this function can describe? It can describe, for example, a coin. Either fake or genuine or fake coin. Like a coin with like a normal coin with two different sides, it would be genuine. Otherwise, a coin with two exactly the same sides, it could be like a fake coin. Okay, so and one can ask how we can define the type of this coin. And classically, of course, what we can do, we can simply look at one side of the coin or look on the another side of the coin and check if these two sides of the coin different or not, right? So it's equivalent to two measurements of the coin, or in our case of this function, of this oracle function. And this Deutsch algorithm claims that we can define the type of this function, like, or the type of this coin in a faster way, in a more efficient way. All right. So let us discuss the Deutsch algorithm step by step and draw the corresponding quantum circuit. All right, so as usual, we start from state 0 and 0. And then in the second qubit, we turn it into the state 1 by applying the X gate. Okay. So here in this side, we still have 0, and here we've got 1, state 1. So then next, we apply the Hadamars to the first and to the second qubits. And as a result, we get here on the first one, we get 1 over square root of 2 state 0 plus state 1. And second turns into the state minus, which is 1 over square root of 2 state 0 minus state 1. Right? After that, we apply a function, the unitary operator, with the properties we are going to describe in a minute. Okay, so we apply some function UF. Okay, so the type of this unitary operator depends on the function that we are defining, but so we don't know the function, but we can encode this function into the unitary operator that acts on these two qubits in a way we're gonna describe. But before that, let us write down the state exactly at the input of this gate. Okay, so let's call this let's call this input as a X input, and this one is a Y input. And let's also write down the expression for this psi, let us call this psi1 state at the entrance to the, at the input to this unitary operator. Okay, so this psi1 is gonna be just the tensor product of two states of the first and the second qubit. So first we write the second one. So it's going to be 1 over square root of 2, then state 0 minus state 1, then tensor, and the state of the first one. 1 over square root of 2, state 0 plus state 1. All right. So I take the tensor product. So it's going to give me a 1 over 2, and then states 0, 0, plus state 0, 1, minus state 1, 0, minus state 1, 1. Okay, so this is the state of the system of two qubits exactly at the input to the unitary operator UF. So now what kind of operation performs this operator? So the operator UF, which we don't know what it is because we don't know the type of the function f. Okay, but this operator is defined or designed in a way that it has no effect on the state on the x qubit, has no effect on x qubit, which is the upper one, but performs the operator, performs the operation y plus modulo 2 or addition modulo 2 fx on the y qubit. Okay, so this operator leaves the x qubit, which is upper qubit, unchanged, but changes the state of the y qubit, which is the lower one, depending on the state of the x qubit. Okay, so it's a definitely gonna be, definitely uses the 2-qubit gate operations, and the result depends on the state of the first of the x qubit. So what is the addition modulo 2? Just remind you that modulo 2. Just remind you that plus and plus gives us plus, right? 1 plus 0 gives us 1, but 1 plus modulo 2, 1 gives us 0. Okay, so this is how it works. So using this property that we just defined, let us write down the state of the quantum system exactly right after the operation, this unitary operator at this side. So this is the psi 2. Let us write down this psi 2 state. So the psi 2 state is equal to 1/2, right? Then, so remind you that first we write the x qubit, then the y qubit. Okay, so the x qubit is left unchanged, but y qubit changed to the state, the first one, 0 plus modulo f and the state x, which is in this case 0. Okay, so this is the state y, and by comma I separate the states of the qubits y and x. So I put comma and then state of the x qubit. So this is the first one, and likewise for the other three. So the second one is 0 plus modulo f1 comma 1 minus 1 plus modulo f0 comma 0 state, and minus 1 plus modulo f1 comma 1. Okay. So how we can simplify this? We can notice that, for example, this part 0 plus modulo 2f0 is just the state f0, right? Because plus 0 doesn't change the thing, and we can rewrite this and as well as here, right? So this is also f1, but the rest two, 1 plus modulo f0 and 1 plus 1 f1, it of course depends on the value of f0 and f1. All right, so we can rewrite this as 1/2, then state f0 0 plus state f1 1 minus 1 plus modulo f0 0 minus 1 plus modulo f1, 1. Okay, so now let us consider the two options, either constant function or constant function or balanced function, this one and this one, these two options separately. So let's start with the constant function. So if fx is constant, function, then what it means? It means that f of 0 is equal to f of 1, right? So the output doesn't depend on the value of the input of the x. All right. So using this property, we can rewrite this state psi2, and let's denote it by constant. If the function f is constant, like as follows: 1 over 2 over f of 0, 0 plus f of 0, 1 minus 1 plus modulo f of 0, 0 minus 1 plus modulo f0, 1, 0, 1. All right, how we can, let's see if we can factorize this parenthesis. And indeed, we can write this as the product of, let us see, as a product of f0 state and minus 1 plus f of 0 state, tensor product state 0 plus state 1 plus state 1. Right? So let us see. The product of the first one with the first one and the second gives us f0, 0. Then the second one, f0, 1. Next, minus 1 plus f0, 0. Minus 1 plus f0, 1. Yeah, so this is exactly the same. Divided by the tensor product. All right, so now we can see that this is in the end the state of the first qubit, the upper qubit, is the Hadamard state, right? The superposition state. And if I apply the Hadamard gate to the first x qubit, it will give me the state 0. So if I put the Hadamard gate here, and then measure the state of this qubit, it will give me 0 state. It will give me 0 state. So let us write it like measure returns 0. So if the result of the measurement of the circuit is 0, then the function is constant. If the result of measurement is 0, then the function is constant. then the function is constant. Okay, so this is the first option. We have another one. We have the option if the function is balanced. So if on the contrary, the function f of x is balanced, that is f of 0 and equal to f of 1. Then we can write this function f of 1 as 1 plus modulo 2f0. Okay, so since the function can get either 0 or 1, then definitely f of 1, or obviously f of 1 can be rewritten as 1 plus modulo f0. So if f0 is 0, then f1 is 1. If f0 is 1, then f1 is 0 because of the properties of addition modulo 2. Addition modulo 2. So in this case, we can write this state 2 in the balance case. So psi 2, I remind you that this is the output of the unitary operator u. So this state can be written as 1/2 let me rewrite what it is. Yeah, this pink one. So 1/2, then f of 0 plus f1 1 minus 1 plus f0 minus 1 plus modulo 2 f1 state 1. State 1. So now we use this property that in the balance case, the value of the function f1 is equal to 1 plus modulo 2 f0. To represent this, to substitute this for the state for the function of f1 here, and here. Okay, so it's gonna be equal to 1/2, then function f0 comma 0 state plus state 1 plus modulo 2 f0 state 1 minus 1 plus f0 0 minus state 1 1 plus modulo 2 1 plus modulo 2 gives us 0 plus f0 modulo 2, which is equivalent to f0, just the value of f0. State 1. Okay. So now we can rewrite this. We can factorize this by the product of two states. with the following questions. So the first one gonna be state of 0 minus state 1 plus modulo 2f0 state, then the product of 0 state minus 1 state. Okay, so let us see. So indeed, the product of the first one, f0 and 0 gives us 0, f0, 0. Then the second one, f0, the minus f0, 1, which is this term here. So the next one is 1 plus f0, 0 with minus, which is this one. And finally, plus 1 plus f of 0, 1, which is this one. So again, here in the second qubit, I noticed that the state of the first qubit, of the upper qubit, is the Hadamard state, the perfect superposition, but the different sign with the minus. And if I apply the Hadamard gate to this one, to the first qubit, I will get the state 1 here. And then if I measure the circuit, I will get the 1 in the output, right? So measure gives me 1 in this state. So if the function f, or let us say, if the measurement gives 1, we conclude that the state or the function is balanced. The function is balanced. So once again, we have a quantum circuit, and the only part to design of this circuit is this unitary operator UF, okay? And the purpose of this circuit, of this algorithm, is to define whether the function f, the oracle, is constant or balanced, depending on the type of the response of this function. Either it's constant in the constant case or balanced, which the result depends on the argument 0, either 0 or 1. We have this function, and we don't know what kind of function it is, what kind of oracle it is, but we can map this function, this oracle, on the quantum unitary operator, this UF, okay? So different kind of functions, f will get different type of the operator, but we don't know the operator. And what we do now, we starting from state 0, 0, we first convert the state of the second qubit, then apply the Hadamard gates, make the superposition of the two, apply this operator UF, and then apply the Hadamard operator to the first qubit. And after that, measure the first qubit in the basis 0, 1. And if we get 0, we conclude that the function is constant. If it gets 1, our function is balanced. The key point here is that we do these both operations simultaneously, like in one single run, one single call of the function u, or this operator u. So it's kind of doing this this measurement or exploring the both opportunities simultaneously. Okay, so in the classical case, as we discussed, in order to define the type of the function requires two calls. In the quantum case, we can do this measurement at once. Okay, so this is the this is the clear demonstration of the quantum parallelism here. So we explore both scenarios simultaneously. And as I said, this function, this oracle, can be seen as a coin, either fake coin when the both sides of this coin are the same, okay, or genuine coin when this is the like a truly, like a usual coin with two different sides. And in some sense, this Deutsch algorithm works as follows. I like this picture, this representation, because it demonstrates nicely the point. So let's say that we really have a coin. Okay, so like a coin like this, and it gets one side of this coin with some profile in it, right? So like a portrait of a, I don't know, like a president or some numbers there. And it gets another side of the coin. And classically, we would need to look at the first side of the coin, then the second side of the coin, and then compare the two, and then see if the coin is good or fake. But alternatively, we can send a wave, like a light, for example, like from a laser, like this. So this is the front of the wave. And the fact that the sides of this coin gets different, or I mean, they have some sort of profile, some corrugation. This corrugation makes the light, this profile makes the light scatter to different directions from the upper side, from the first side of the coin, and from the second side of the coin. Okay, and then I have for example, a screen here, and the key point here is that the light is like a light of a laser is coherent, and it can provide a interference, right? It can interfere. So these two beams, they can interfere with formation interference pattern, right? So if the coin is fake and the two sides are the same, then these two scattered beams will be the same too, and they will provide some sort of symmetric interference pattern like this. And this would be indication that the two sides of the coin the same. However, if the two sides are different, then the interference pattern will be different too. And for example, it can be something like this, for example. And this is the clear indication that the coin is fake. The coin is the genuine. So it's a good coin with two different sides. So it's a nice demonstration of how the property of interference, the property of coherence, allows more efficient calculations or like measurements. For example, yeah. So as I said, this Deutsch algorithm rather useless. I mean, at least I am not aware of any like practical applications of this algorithm, rather than using this algorithm as a benchmark for quantum computers. So the Deutsch algorithm itself is rather trivial because it is just two qubit circuit, and we cannot even use this algorithm for benchmarking computers. There is another one, like a generalization of a Deutsch algorithm, and it's called Deutsch-Josa algorithm. So let's call this one 4.41, for example. Deutsch Josa, like this algorithm. So Josa algorithm is just generalization to n qubit function, n bit function. Generalization of Deutsch to n bit functions. Okay, so how does this n bit function works? This oracle. So the oracle function f in the n bit case gets the n bit string as an input, 0, 1, n lengths. Okay, and returns just either 0 or 1, this oracle. And the generalization of the circuit would look like this. So again, we start from qubits in the state 0, 0, and then we have the state, or like n qubit state for the upper state, for the upper system register, right? Then we apply the Hadamard. So in this case, it is Hadamard to the power of tensor n. Okay, so we apply the Hadamard to all of these qubits in the register. Meanwhile, we apply the x qubit to the second one, and also Hadamard to the lower one, to this y qubit. Then here is this unitary operator UF, which again we don't know, and to be defined. We call this one is X state, this one is Y state, and this operator returns the X to the output here, but output here is equal to Y plus modulo 2F state X. Okay, and then we apply the Hadamard to the power of tensor n to the upper one, and measure the state of this n register qubit, or the system of qubits. And this allows us to define the type of the oracle, either constant or balanced. So a few words about complexity. So the classical problem requires the number of calls to this function of the order of n, right? So this is the complexity of classical problem. In quantum, in contrast, we have this complexity of the order of logarithmic n. Complexity. So for the case of 2 qubits, it's rather trivial, right? But in contrast, if we have the number of states, different states of 10 to the power of 10, for example, the ratio of these two complexities, the 10 to the power of 10 here and logarithmic 10 to the power of 10 here, gives us a factor of 10 to the power of 10 to the power of 9, right? 10 to the power of 9. So this is 10 to the power of 9 times of speed up. Speed up of the quantum algorithm comparing to the classical one. So here at this point, I also must note that there are some works that have demonstrated that using just classical computer, classical machine with provided randomness, like classically provided randomness, allows to mimic this Deutsch algorithm in some certain way. So people still investigate this type of algorithm, and there are some debates around these numbers, like what's exactly the speed up. Okay, so definitely for the systems with a number of qubits rather than 30 or like 40, the quantum algorithm is the only possible algorithm, because, for example, if you use a classical computer to mimic or to simulate a quantum machine, like quantum machine, when you so when you simulate a quantum machine using classical system, you need to keep in memory all the states of 2 to the power of, let's say, 30 amplitudes of the quantum computer. And at some point, your computer doesn't have enough memory. For example, today's supercomputers, they can keep in the memory the state of roughly 2 to the power of 60 amplitudes. So today's classical supercomputers, like Google supercomputer, can simulate and simulate in a very inefficient, very time-consuming way a quantum computer of maybe just 50, 60 qubits. And of course, 60 qubits is rather simple. Today we have quantum machines with, for example, 400 qubits, and people develop systems with 1,000 qubits. And 1,000 qubits, by the way, 2 to the power of 1,000 is already more amplitudes than particles in the world, right? In nature. So, but still, people develop, people investigate this type of quantum algorithms, as well as all other algorithms, and there are some debates about what is the actual speed up and so on. So let us transit to the next algorithm, which is Shor's algorithm, and I'm gonna discuss just the purpose of this one. So let us discuss the Shor's algorithm. So the Shor's algorithm is very much connected to the Fourier transform and the quantum Fourier transform. And before discussing this Shor's algorithm, let us ask ourselves if we can use quantum computers for maybe more efficient Fourier transform Fourier transform analysis. So you know that Fourier transform, when you have some, for example, some sort of spectrum or some data, some image, some like sound, whatever, some information, and the Fourier transform allows you to do a lot of things, like many things. I would say that Fourier transform today is the most important thing in engineering, in many areas. When you deal with like sound analysis, communications, computing, spectral analysis, when you archive data like images, uncountable areas. So in all these areas, you use the Fourier transform and different like variations of Fourier transform, like fast Fourier transform. So Fourier transform is extremely important. And one would say that it would be extremely useful, beneficial to use quantum computers to do the Fourier transform of data. And unfortunately, so let us write this down. So can we use quantum computers for taking the Fourier transform? Can we use quantum computers for the Fourier transform? In an efficient way. And unfortunately, answer no, because in a simple way to answer to this question is to say that for the Fourier transform, we need all the quantum amplitudes. For example, for a computer with n qubits, we need 2 to the power of n amplitudes, and we need to know all of them. And however, when we measure the qubits in their states, they collapse to the one of the computational basis states, right? So we lose the information. One can do this approach of quantum tomography. So there is an approach of quantum tomography which allows to restore the quantum state after multiple measurements of the same system. Like you prepare the state of a multi-qubit system, you measure it, then you prepare it again, you measure, prepare again, measure, do the statistics, or you entangle this system with a part of another system and measure the other system. Anyway, so there are different approaches to restore the information about the of the quantum of the quantum state. So at least potentially we can get the information about 2 to the power of n amplitudes. However, in the case that might be practically useful with the number of qubits over hundreds, this would require a lot of classical memory to store the information about all these amplitudes, and it definitely not more efficient than just classical Fourier transform. Okay, so let us write this down. The answer to this question, no. Because for the Fourier transform, we need all to the power of n amplitudes. Because for Fourier transform, we need all 2 to the power of n amplitudes. Okay, and we either lose this information after the measurement, or we can restore this information by multiple measurements and doing this quantum tomography operation, but it requires a lot of computational memory, so it's not practical, not feasible, and definitely not useful. So yeah, so no speed up for the quantum transform, which is very pity, because one would really need a machine that does this Fourier transform in an efficient way. So no quantum speed up for Fourier transform. However, quantum computing can find the periodicity of functions, of data, or of a set of numbers, which is a simpler problem, right? So Fourier transform, what it does, it also finds the patterns, right? For example, in this typical Fourier transform of when you have a signal, like a sound, and then you Fourier transform the sound, and you get the different amplitudes, Fourier transform amplitudes, like sine and cosine function that contribute to that sound, right? So you find you represent the signal as a combination of other periodic functions. We cannot improve that process with the quantum computer, but quantum computer helps us to find the periodicity in the data. So let's say you have a long or large number, or a list of numbers, and the quantum computer can find the periodicity in this data. So let us write this down like this. However, quantum computer can find the periodicity in a set of integer numbers. In efficient way. So where it can be useful? So this can be useful for, it's claimed to be useful for factoring a number, which is a product of two prime numbers. Okay, so this can be useful for factoring numbers, for factoring a number which is a product of two prime numbers. Of two prime numbers. So what is a prime number? Prime number is a number that is divided by itself and one, right? And nothing else. So for example, 1 is a prime number, 2 is a prime number, 3 is a prime number, but 4 is not a prime number because 4 is divided, can be divided by 4, by 1, and also by 2. So 7 is a prime number, and so on. And one can use, for example, Mathematica, this Wolfram Mathematica, to factorize the numbers, including some large numbers. For example, if I use this command, this Mathematica command factor integer, for example, of 10, right? It will give me what? It will give me 2 to the power of 1 times 5 to the power of 1. So I take 2 ones and 5 ones, take the product of them, and it gives me 2. So this is the representation of 10 as the product of two prime numbers, 2 and 5. Likewise, for factoring, for example, 30, it will give me what? It will give me 2 ones times 3 ones times 5 ones. 2 times 3 is 6, 6 times 5 is 30. So it works pretty well for like small numbers, but try to take two rather long prime numbers. Prime numbers like with 10 digits or 15, 20 digits, and take the product of two. So this taking of the product of two prime numbers is pretty straightforward, right? So it requires just a millisecond of computational time. But then try to factorize this prime number using the same function, factor integer, and it will take much longer time. So it's a example of operation, mathematical operation that is very straightforward in one way, but very time consuming, very complex in the way around. And where it's used, this operation, this type of approach is used in the as a basis for this RSA encryption security method. Right. So the RSA, this RSA stands for the first letters of the engineers who came up with the approach. RSA encryption security method. So this in RSA security method, it consists of in generating of two prime numbers, which called, first of all, there are various approaches to this method. Here is the simplest one. So you generate just two sufficiently long prime numbers. One is the encryption key. Which is public, right? And another one is decryption key. Which is secret number. So you basically have a decryption key, okay? Then you have a generator that generates the sufficiently long prime number, and then you take the product of your the decryption key with the long prime number, and this way you get the encryption key. And this encryption key can be shared publicly, can be transmitted in a like through an open channel, information channel, because this is the long prime number that is very difficult, like extremely difficult for factorization. Okay, so you cannot factor this very long number. On the other hand, since you have this decryption key and you receive the encryption, and using the decryption key, you can easily calculate compute the second part of this number. Okay, so the second prime number of this number. So the Shor's algorithm has a very it's very connected to the Fourier transform, like Fourier connected to the problem of finding the periodicity in strings of numbers, let's say. And it's proven to be useful for finding the prime numbers and factoring like large prime numbers. Okay, so the purpose of this algorithm is to find factoring the large prime numbers, or numbers that are composed of like a the product of two prime numbers, and this will probably lead to the need for new types of security approaches. Okay, so if we get sometime like in the future, if you get the powerful computer enough, quantum computer, it will allow us to find it will allow us to factoring the large prime numbers, or large numbers that are product of two prime numbers, and we will need to come up with other approaches for security. All right, so this is the I mean, in short, about the purpose of Shor's algorithm. Another type of algorithm, which is chapter, it's not chapters, like a subchapter 4.6, is known as quantum Fourier transform. Quantum Fourier transform, or QFT. So quantum Fourier transform doesn't have its own purpose. It is rather used as a as an element in other quantum algorithms. Okay, and essentially the quantum Fourier transform is just the change of the basis from computational state to the new basis, to the Fourier basis. In some sense, the classical or conventional Fourier transform is also a change of a basis. For example, if you have some signal, like in time domain, right, you can apply Fourier transform and transform this time domain to frequency domain representation, which is in some sense the change of the basis of the description. So conventional Fourier transform is the change of basis. Well, for example, from time to frequency, right? So the quantum Fourier transform is also change of a basis, but the quantum basis of the quantum state. Quantum Fourier transform is also a change of basis from computational to the Fourier basis, to the Fourier basis. So let me write down the formula for this Fourier transform. So the formula is like this. So for the Fourier transform for Fourier basis, I denote this Fourier basis by the tilde above the state. So this is the state X. This is the state of a n qubit general quantum system. Okay, so this can be like a very long string of zeros and ones which encode the quantum state. And this is the QFT of state X. State X, again, this is the well, in this case, this is the state X denotes the computational state. All right, and this Fourier transform is given by this simple formula 1 over square root of capital N, which denotes the number of amplitudes of the state, and then summation which runs from the y0 to n minus 1, then e to the power of 2 pi I x times y over n state y. The state y denotes the computational state. In a system of n qubits, we have n capital equals to 2 to the power of n, right? So this n capital is 2 to the power of n, and the summation runs over all the possible computational states. And this is the result. So for the it's instructive to write down this formula for the single qubit system. For example, for one qubit, when n capital is equal to 2 to the power of 1, which is 2, right? We can write the QFT of the computational state using this formula, like y from 0 to 2 minus 1, which is 1, right? Then e to the power of 2 pi I x y over 2 state y. So in this case, we have two terms, 1 over square root of 2. Then in parentheses, I get e to the power of 2 pi I x times 0, right, for the first state. for the first state, because the computational basis here for the first for the single qubit system, computational basis is state 0 and state 1. Okay, so just two amplitudes. So it's 0 over 2 and state 0, and then plus e to the power of 2 to the power of e to the power of 2 pi I x times 1 over 2 state 1. Okay. So now I see that this is this phase multiplied by 0, so this one is equal to 1, and this part is equal to e to the power of I pi x. Okay, so it's equal to 1 over square root of 2, then state 0 plus e to the power of I pi x state 1. Okay, and now by components, I can write the QFT of the QFT of the state 0, for example. What I get? 1 over square root of 2, then state 0 plus e to the power of I pi 0 times 1. So it's perfectly equal to 1 over square root of 2 state 0 plus state 1. The Hadamard state, the superposition state of two computational states. And the QFT of the state 1 is equal to 1 over square root of 2 state 0 plus e to the power of I pi state 1. So this e to the power of I pi is equal to minus 1, and I get the state minus here, right? So indeed, this QFT for the one qubit system is just transformation from the computational 0-1 basis to the Hadamard basis, to the plus minus states. In the case of n qubits, it works similarly, and similarly, the only maybe point here is to say about this xy product, right? So in case of multi-qubit system, this is this product of xy is should be considered as a inner product of two vectors by components. Yeah, so this is pretty much it about the quantum Fourier transform. And let us maybe transit to another one, 0.7. Let's call this quantum random circuit. Quantum random circuit. So what is quantum random circuit? So essentially, this is just another benchmarking algorithm. Another benchmarking algorithm. So, for example, it's used to demonstrate the quantum supremacy in 2019 by the company by Google. right? It's used to demonstrate to rate the quantum quantum supremacy. In 2090. By Google. So what is this about? It is just, it's not really an algorithm. It's like rather a circuit with now a number of unitary operators. Let us draw them, for example, like this. So, for example, I have one unitary operator here, and then, for example, I have other qubits here, and applied some another unitary operator here, and I might have other qubits in the system, and for example, I can apply it then in another time moment. I can apply another unitary operator here, and for example here another unitary operator like this, and then I can again apply it like this, and like this. So essentially it is a sequence of applications of unitary operators in a random way, and also application of measurement operators in different parts of the circuit. Like, for example, I can measure the circuit here. In the next time moment, I can measure the circuit here, and I can also measure it here. So this red gates demonstrate the measurements of the different parts of the circuit in a different time instance. Okay, so so the application of the unitary operator changes the wave function. Then I measure, or my circuit measures the different qubits in this register, and which is essentially the projective measurements, right? So it collapses some parts of these functions to some other computational basis, let's say, and then unitary operator again mixes the states up, and then the measurement again collapses some parts of these functions. So, and essentially it's a complicated, complex circuit with many qubits and many unitary operators and measurement operators applied to this circuit in order to mimic a sort of random walk. Okay, so for example, if I denote the time instance of this one here, this one, so different time instance in the circuit, I will get the evaluation like schematic, very schematically, the evaluation of the psi vector of the psi state, something like, for example, like this, right? And it reminds the random walk, but for the wave function of the wave function and the point is that we can, for example, develop a circuit with, for example, 50 qubits, and then do these different unitary operators, measurements, etc. And it represents the quantum walk like a very complicated process. And the point is that starting from a number of qubits around 50, no classical computer that can simulate this random walk like classically, but at the same time the quantum computer can do this random walk easily. Okay, so and in 2019 this company Google, they published their results on the on this quantum random circuit analysis and simulation using classical supercomputer, and they claim the quantum supremacy in their famous Nature paper. I must note, however, that after publication that paper, there was many other works that claim that it was not a truly quantum supremacy, because using other approaches, one can still simulate this random walk of quantum wave function using classical computer and so on and so forth. But anyways, today we have computers with 400 qubits, and they are definitely not reachable by classical machines. Okay, as I said, in order to simulate a quantum computer classically, you need a computer with a memory enough to store the all 2 to the power of number of qubits, number of amplitudes, which is not possible for classical computer. Right, and for the sake of completeness, let me also quickly tell you about these quantum simulation algorithms. So let's put this chapter 4.8, simulation of quantum systems. Simulation of quantum systems. And the most important one is the variational quantum eigensolver. Or VQE. VQE. So VQE allows one to define the, for example, the ground state of a molecule. And this is extremely important for designing molecules, designing chemicals, and in particular for designing medicals, right? Like instead of developing the medicine from scratch using different materials and doing a lot of medical tests, first on animals and then on humans, people. Instead, researchers in this quantum area, they develop or dedicate a lot of effort to developing the approaches, let's say this way, developing approaches to engineer molecules, engineer chemicals, engineer medicines, in a reversed approach. Like you know the properties of a desired molecule, and then you design it and investigate it and using, for example, the quantum computer. And there is this very useful variational quantum eigensolver, which allows us to compute the, for example, the bounding energy of different molecules. Like if I have a molecule of one sort and then molecule of another sort, oops, like this. Okay. And then, of course, if they interact in a way, or if they form the stable molecule from these two atoms or two other molecules, right? The energy of their interaction could look something like this. So this is the distance, this is the energy, and then if this state is bound, then the energy profile as a function of distance would look like this, right? The zero when they are set apart, then the negative energy that corresponds to the bounded state of the molecules, and of course this energy grows if we bring the one part of the molecule to the rest. And so this is the ground state of the bound state of this molecule, and the existence of this state and the energy that this molecule acquires in this state is very important for chemical reactions, because in the end of the day, the chemical reaction is just exchange of molecules, and the bounding energy between different molecules, different materials, chemicals, it affects the all properties of the chemical reactions, like a rate of chemical reaction, and so on and so forth. So having such a variational quantum eigensolver, so this eigensolver, this quantum eigensolver, allows us to compute the states of molecules, like of complex molecules. All right. There are some tutorials on YouTube, for example, about this quantum algorithm that I refer interested people to. And this is basically the end. That's all what I wanted to discuss today. And this concludes the part about the quantum algorithms. So the rest of this course, this maybe two last classes, right? We're gonna dedicate to the hardware of the quantum computer. So we will discuss very well quickly the different approaches, different types of hardware of quantum computers, and in a very general way how this hardware work. Okay. All right, so this is the end for today's lecture. Thank you very much, and let me stop it and see you next week.